Okay. 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 Good morning, everybody. I am Andres Santander. I'm very happy to be here. Thanks to the organizers for this fantastic invitation. This is the second time I am in Natal, and as I remember from last time, we always have a lot of fun. So I am expecting to have also a lot of fun today. This is a very long title, indeed. I will try to make 2 stories into a half an hour slot. When I was invited, I was told at the beginning that I had 1 hour, and then I learned 2 weeks ago that I actually had half of that time. Anyway, I will try to be as pedagogical as possible. Today, we will be speaking about, let me see, okay. We will be speaking about 2 subjects. The first is hidden order transition in uranium-ruthenium-2 silicon-2, which we learned something from the previous speaker, so I will take advantage of that momentum to rapidly introduce the subject. And the second is the 2-dimensional electron gases in transition oxides. Okay, let's start with some rapid details about the experimental technique that we use in our group. Is angle-resolved photoemission spectroscopy, ARPES. So the details of the technique are really simple. We shine with ultraviolet photons our sample, and by photoelectric effect, electrons are ejected from the sample. And what we do is we measure the kinetic energy and the angle of ejection of those electrons with respect to the normal to the surface. And by 2 very simple conservation laws, the conservation of energy and the conservation of momentum, we can immediately infer what was the binding energy of the electron in the solid and the component parallel to the surface of its momentum. And then, like that, we can measure the electronic structure of the material. This is a beautiful example in a simple case. This is what you expect theoretically from the 111 surface state of copper. It's just a revolution paraboloid. It's a free electron-like state. And this is what you can experimentally obtain. So what you see here in color scale is the probability of measuring 1 electron for a given, for a given binding energy, okay? For a given binding energy and momentum. I think I will shift to the laser. This is the laser. Okay. So this is the binding energy and momentum. And what you see here is a beautiful free electron-like parabola and the Fermi surface that looks like the circle. So what we learned in basic solid-state physics about a free electron. Okay, so let me start with the first subject, the mysterious hidden order transition in uranium-ruthenium-2 silicon-2. This subject was the PhD work of these 2 students, Cédric Barret, who is now postdoc in the University of Tokyo, and Florine Boario at the University of Würzburg. And it was done in collaboration with researchers at the NEEL Institute. And actually, most of this work was already published a few years ago, but I have found it very surprisingly that it is still unknown to a large part of the uranium-ruthenium-2 silicon-2 community. So I will talk about it again. Okay. Let me briefly remind something that we already saw in the previous talk. Uranium-ruthenium-2 silicon-2 has a body center tetragonal structure. This is how the Brillouin zone looks in reciprocal space. We will be looking at the electronic structure mainly in the plane at the center of the Brillouin zone. So the plane going through gamma is the blue plane here. And because of the structure is body-centered tetragonal, the Brillouin zone tessellates a reciprocal space like the bricks of an orange brick wall. So it's alternated like that. So when you go through the first Brillouin zone in the plane, you see this polygon and then this square. It was very early recognized that when you cool down the material, there is a transition to a yet unknown state at 17 Kelvin at ambient pressure. And then when you apply pressure, this hidden order state eventually becomes a true antiferromagnetic state. We will be talking about what happens at ambient pressure. Okay. And another thing that is already known since almost the very beginning of researching this material is that indeed, so this is specific heat C over T versus square temperature, and you see a beautiful second order phase transition here. There are two important things that I will be showing in a minute, how beautifully they appear into the electronic structure of the system. The first thing is that when the transition happens, the fit to the exponential decay of the specific heat immediately tells you that there is an energy scale of about 11 millivolts of a gap opening somewhere in the electronic structure near the Fermi level. And we will see that we can beautifully retrieve this energy scale in the electronic structure data. And the second thing that is evident from the data is that from the difference between the Sommerfeld coefficient at high temperatures and low temperatures, this is, you see, is about half of it. It was already mentioned in the previous talk. So about 40 to 50% of the Fermi surface seems to be gapped when the system undergoes the hidden order transition. And again, we will see how beautifully this appears into the electronic structure data. And to not keep you anymore with the long story, this is a brief show of the most important data that we measured. So this is the Fermi surface changes across the hidden order transition as measured by high resolution, low temperature photoemission. The data that you see here are at 20 Kelvin, and the data that you see here are 1 Kelvin data. Let us first take a look at, so this is the first Brillouin zone, at what happens along this direction, the 110 direction. We can see the dispersions near the Fermi level here and here at 20 Kelvin in the paramagnetic state and 1 Kelvin in the hidden order state. And you can immediately see that even if you forget the red lines that I put there to serve as a guide to the eye, there are huge changes going on. So indeed, experimentally, we can observe the changes induced by the hidden order transition into the electronic structure near the Fermi level. Here you see a very heavy state, which in electronic structure terms means a very small curvature near the Fermi level. You see that the state stops here and here, so you can take these two as the Fermi momenta. And if you actually try to fit it with a parabola, it gives a very heavy mass. But you see that when the system undergoes the transition, this state transforms into this M-shaped state with a light, small pocket here, and then two states here. And the most important feature is that here, at the Fermi momenta, a gap of 7 millivolts appears. So the gap that was seen 30 years ago by a specific heat, or inferred from a specific heat, is directly observed in the photoemission data. And the second important thing is that that gap is anisotropic. If you look here at 20 Kelvin, you can clearly see that this state is forming a diamond. And this is very important because other probes of electronic structure like Shubnikov de Haas are unable to measure the electronic structure at this elevated temperature. Yes, you can see here, here. It's more clear here in this branch. But you can also say that it should be there because this band is fully filling all the states up to this Fermi momenta. So there have to be states all the way around. Okay? Then when the system undergoes the transition, you can see that there are not any more states here, but there are some states remaining at these corners. So the Fermi surface has undergone a massive reconstruction where most of the states have been washed away, have been gapped by this gap of 7 millivolts, and the only thing that remains are these diamonds. If you really feed the data carefully, what you find is these small petals here. So we call that the petal Fermi surface. And the second important conclusion is that when you really compare, because we can measure it directly, the area enveloped by the Fermi surface in the paramagnetic state with the area enveloped by these small petals, you find that about 30% of the, that about 70% of the Fermi surface of the diamonds has been washed away by the transition, and only 30% of it is remaining in the petals. So indeed, the massive change of Sommerfeld coefficient is again retrieved into the electronic structure changes of measured by ARPES. So I will say that, and now let me also show you how beautifully this data tells us why LDA is not is good, but is not enough to take into account the experimental data. What we see here is a comparison of LDA calculations into what the researchers that did this work suppose was the best approach to the hidden order state. Of course, because we don't know what a hidden order state, you cannot do calculations into the hidden order state. What you can do is assume, and there is a very good hint from Shubnikov that has that it's more or less true, assume that the electronic structure in the hidden order state looks pretty similar to the electronic structure into the antiferromagnetic state. So this is what these researchers did. And then the black symbols are is the Fermi surface in the antiferromagnetic state. The blue dots, it's our ARPES measurement. So you see that it looks pretty similar. And again, here, these are the LDA calculations, and this is our data, both along the the 100 and 110 directions. And you see that it looks pretty similar. Here you have this M-shaped band structure, and also here. But can you tell me what is the main difference between this experimental data and the calculations? The shape is the same. The Fermi momenta are the same because the Fermi surfaces look so similar. So what is very different between the two? Sorry? It looks the same, but it's not. The scale, you see, is 1 order of magnitude difference. And this is a beautiful example of what a heavy fermion material is. In the electronic structure data, the real data from real life, the bands disperse on an energy scale that is 1 order of magnitude smaller than the LDA calculations, which means the mass is 10 times bigger than what LDA will predict. Okay? So this is a beautiful example of why we call this a heavy fermion system and why LDA is a very good starting point, but is not good enough to really picture the whole physics of the system. Okay, yes? It looks pretty similar, at least from an electronic structure point of view. Yes, indeed. Actually, I don't have the time to show that data, but we find that the uh, the electronic structure near the X points here also changes in a way that is not quite the same as predicted by LDA. Okay, thank you. So I think I conclude this part, and I'll try to go rapidly through the second part of my talk. What we observe is that the hidden order transition is accompanied by a Fermi surface instability that is clearly observed in the data. The hidden order parameter is anisotropic. The Fermi surface goes from a diamond in the paramagnetic state to petals in the hidden order state. About 70% of that diamond is gapped with a gap of 7 millivolts opening along the diagonals. And I didn't show it, but the Fermi petals are actually separated exactly by one wave vector that is clearly observed also in neutron scattering data, which is called the incommensurate wave vector. Okay, let me now change gears to the second subject. Let's see how far we can go into it. Because the community here is so diverse, I thought it would be also interesting to speak about this subject, which is the two-dimensional electron gases in transition metal oxides. Why this subject is interesting? It was observed in 2004 that at the interface between these two insulators, lanthanum aluminate and strontium titanate, look at the gap, it's a huge gap, so it's a really strong insulator. At this interface, you can obtain a metallic state. And not only you can obtain a metallic two-dimensional state, but by applying a gate voltage, you can change it from being a bad metal to become a superconductor at very low temperatures. So this is interesting from both fundamental points of view. It's a very interesting state of matter in itself at the interface of two otherwise stupid insulators, but also because two-dimensional electron gases are the source of all modern technology. And in this case, it will be two-dimensional electron gas at the interface of two correlated oxides. However, it is not yet known what is the origin of this metallic state here. And what we realized was something very interesting, is that it is actually not necessary to use these interfaces to create these 2D electron gases. At the very bare surface of strontium titanate, you can already obtain a 2D electron gas. This is the sample that we measured. You see is transparent insulating, like a glass, and yet, contrary to what you will commonly think, its surface can become conductive. And the microscopic experimental proof is here. Again, this is binding energy versus momentum, and you see 1, 2 beautiful light bands and one heavy band dispersing through the Fermi level. And the Fermi surfaces are here, 1, 2 circles due to the light bands, and 2 ellipses due to the heavy bands. If you do reverse engineering of this, for instance, you assume that these states are due to a quantum well in the shape of a triangular wedge, then because we know the energies and Fermi momenta of these states, we can infer all the characteristics of the quantum well, and we know that this corresponds to states that are confined on a scale of about 4 unit cells below the surface of the system. So it is indeed a quasi two-dimensional electronic state. The origin of it is actually very simple, and in this case we know it. It's oxygen vacancies that form very easily with ultraviolet radiation at the surface of the material. And these oxygen vacancies have two effects. They dope with electrons the surface, and they create a positive, oxygen vacancies are positive, so they create a positive background that holds those electrons close to the surface. So the next question that you can ask yourself is, okay, this mechanism looks really simple, and many oxides are really willing to form vacancies. Can we generalize it to other materials? And the answer is yes, it can be done. So far, we have been able to do it in many, many materials, so this is a rapid look of 3 of them. potassium tantalate, due to tantalum, which is very heavy ion, the spin-orbit coupling is very strong in this 2D electron gas, and as you can see, the shape of the electron bands is very different from the one obtained in strontium titanate. For instance, we have one very heavy band, one intermediate, and one very light band. Anatase titanium O2, which is a material that is very important for photocatalysis, is actually the best photocatalyst known so far in the solid state. It's almost like chlorophyll in the solid state. And we found that we can create a 2D electron gas also on it. We are right now exploring how this 2D electron gas might be related to the photocatalytic properties of anatase. And a third material that we explored recently is calcium titanate. Contrary to strontium titanate, in calcium titanate, the structure is tilted and rotated. So you immediately see that instead of having the two circles and two cigars, what you have is two circles, but one flower. And the flower is due to the hybridization of states induced by the tilting and rotation of the octahedra. Okay, so I think at this point, my time is over. Okay, so I will go rapidly through this, and with that, my talk will be over. It turns out that when you create a vacancy in an oxide, you will be changing the valency of the transition metal atom nearest to that vacancy. And that can also have other effects, like inducing magnetism. This was already suspected from the lanthanum aluminate strontium titanate heterostructures that I showed before. For instance, with microsquid rusting measurements of this interface, these researchers were able to measure these magnetic dipoles in this interface. Remember that there is also a metallic state that becomes superconducting at low temperatures in this interface. And now you add magnetism to the story. So we were wondering, can we also observe magnetism in our surfaces? And the answer seems to be yes. Let me first tell you how we did it. We worked in collaboration with the group of laser spectroscopy in Tokyo University, and we use a fantastic tool developed by this young researcher, Toshi Tanuchi. It's laser photoelectron microscopy. So because we use laser with a very low photon energy, electrons from the valence band do not have kinetic energy enough to overcome the work function of the material. Only electrons from the conduction band can eventually be detected. And furthermore, if we use it in circular dichroism mode, so we measure left and right photon polarizations and we make the contrast between them, we can detect magnetic domains. Here is an example of ferromagnetic domains in iron platinum measured by this technique. So we did exactly the same at the surface of a strontium titanate at room temperature where we induced oxygen vacancies. And the result is this. So this is a microscopic real space image of the Stepan terrace surface. At room temperature, you see already a lot of ferromagnetic domains seen by the red and blue colors. If we warm up to 1000 Kelvin, the image looks almost single domain. It's white, so there are no more domains. And actually, to cross-check that this has a magnetic origin, we did the following experiment. We went from room temperature up to 700 Kelvin, applied a magnetic field, cooled down in magnetic field. Photoemission, for technical reasons, cannot be done under magnetic field, so you need to turn off the magnetic field. But then you see that when you measure again, the magnetic contrast has increased after the field cooling procedure. So indeed, this seems to come from magnetic domains. So with this, I end my talk and arrive to my conclusions. Oxygen vacancies in oxide provide a beautiful universal knob to create novel states in these materials. They are able to do electron doping. confine electron doping, confine those electrons. They allow tailoring the electronic structure depending on the material or surface that you are using, and they can even induce magnetism at the surface of these materials. Thanks for your attention, and I would like to show as a last slide my collaborators in my group. Thanks a lot.